Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure I'm Wolfram Schulte from the Foundation of Software Engineering Group, and it's my pleasure to introduce Viktor Kunčák, who is finishing his PhD currently at MIT under the guidance of Martin Ruinart. And I think since we're already a little bit late, let's get started, and Viktor will give a talk on modular static analysis with sets and relations. Thanks a lot to Viktor.
Thank you, Wolfram. So I'm going to tell you how to use modular static analysis to verify data structure consistency properties. And this is joint work with a set of great collaborators that I had the pleasure to work with. So I'll start by just saying a few words about the general area. So this work belongs to program analysis and verification, where the goal is to discover and verify properties of computer systems and software systems in particular. And this area has a long tradition of being both practically relevant. Most of these applications ultimately increase programmers' productivity by either enabling high-level language constructs or most recently there's been clear evidence that the software reliability is extremely important. So these techniques enable us to discover and prevent programming errors or even understand and maintain existing code. And it also has broader implications in terms of analysis of formal artifacts. You can think of just semi-formal and formal documents like XML documents, proofs, designs, and so on. So being a large area, there is a wide spectrum of existing analysis techniques. There are techniques that are focused on finding large numbers of bugs, but there are also techniques whose goal is to prevent bugs from happening in first place. And we've seen a lot of success for control-intensive applications that have finite state, such as model checking. And one of the goals that is a challenge nowadays is coming up with techniques that are effective for data-intensive applications that manipulate complex data structures. And in general, we could talk about techniques that address some language-specific properties that you could derive without any additional specifications, or some properties that are actually specific to the application that you are verifying. And of course, this is a long-standing goal in this area is full program verification, being able to verify that program does what we would really want it to do, where, for example, what we would want it to do is described by a complete specification. But in reality, what we have found to be more successful is verifying some key partial correctness properties. And a success story here are type systems that are used in modern programming languages. And we have seen a lot of work in some temporal properties that verify ordering of certain actions in the program. And now the challenge is how to go beyond these finite state properties that are flow sensitive. So basically going to something that allows us to track values and relationship between different values. And this brings me to the area of verifying data structure consistency properties. And so this is what this talk is about. So I here present a few examples of consistency properties of data structures. You can think of a linked list. If it's a doubly linked list, then one consistency property is that pre-field is inverse of the next field. Or if you follow the next field, you don't get to a cycle. So the next field is acyclic. Or if you have another data structure that has two pointer fields, left and right, then you may want to ensure that it actually forms a tree. So in fact, if you look at some data structure that has two pointer fields, it might end up being a linked list or a tree because type systems don't tell you that kind of information. So it's really some shape information that we would like to know in order to distinguish these kinds of data structures. And note that these are properties that change over time and that involve potentially an unbounded number of objects. So we don't know at compile time how many objects they will involve. And so in addition to these sort of shape properties, we're also interested in properties that correlate some numerical quantities with the objects stored in data structure. So if you have a size field in container implementations, and this, if you look at common library implementations you typically do have, then you would like this size field to be consistent with the number of elements that is stored in the data structure. And so this is another example of data structure consistency properties. And clearly bad things happen if the data structure consistency is violated. So a program might crash if you follow a pointer that is not pointing where it should, or simply if you execute an operation that's written assuming the data structure is consistent, then the result of that operation might not be what you want. For example, you might end up accidentally removing multiple elements or not inserting an element into the structure. Or if the structure is cyclic when you don't want it to be cyclic, then you might end up looping in your code. And these are all examples of internal data structure consistency properties. So by that I mean properties that talk about what's happening inside one data structure. And in addition to these properties, we are also interested in external data structure consistency properties that correlate multiple data structures. And these are properties that are ultimately relevant to the developers and even sometimes users of the system. So here I show an example of two sets of objects, person and book, and a binary relation borrows. And you can think of this as a fragment of some library system. And one of the consistency properties here would be that if there is a pair in the relation, then the first component of the relation is in the first set and the second component is the second set. So you could think of this as a database relational integrity, or basically a semantic counterpart of absence of dangling references. So these are also properties that we would like to verify. And then once you have these kinds of properties, then you might want to ensure some cardinality constraints. For example, that the inverse of this relation is functional, so that you cannot have two persons checking out the same book, or that one person can check out at most 4 books at a time. And so these are, you can see that if you violated some of these consistency properties, you might actually have some security violation, or basically violate application-specific policies. And so although we are ultimately, in some sense, interested in these high-level external consistency properties, we also need to verify implementations of these sets and relations that are needed in order to implement these high-level concepts. And this is why we are interested in both internal consistency and external consistency properties. So our goal is to prove such consistency property in all program executions. So we don't want to just find bugs. And we want to do that with high-level automation. So not, for example, doing interactive theorem proving everywhere. And we would like, as I mentioned, both internal and external consistency is relevant. And it turns out that in order to do that, to do this verification, you need to verify both the implementation of data structures and also the way these data structures are used. So basically protocols for using data structures. And so how are we going to do that? So we want to build a static analyzer that's going to take as input source code of the program and a description of consistency properties. And it's going to say either the data structures are consistent, or it's going to indicate a potential error in the program. And so what are the challenges in designing such a static analysis system? Well, if you have a program with complex data structures, then you cannot really use some simple analyses that have traditionally been used in compiler optimizations and in static analysis community. It turns out you need typically analyses that are more precise than that. And also, you cannot expect that a single approach will work, because there are so many different kinds of data structures. And finally, because we want to verify these data structures in the context of larger programs, we need to have some way of addressing scalability problems. And as I mentioned, we want to check actually user-defined properties as well, because those are the ones that tell you something with respect to whether the program is doing what we want it to be doing. And so I'll explain you the key ideas of our approach through an example. And so this is actually talking about data abstraction capabilities and how we have incorporated it in the context of static analysis system. So the example that I'm going to use is a Minesweeper game that we wrote and implemented in our system, so you can download it and run it in the interpreter. And Minesweeper is interesting because it has some data structures. Mainly the key abstraction that Minesweeper has is the cell object. And there are several data structures associated with the cell object. Namely, there is an initialization flag that we set to true when we initialize the object. There's also isExposed flag that distinguishes these cells that have been already exposed from the cells that are still hidden. And then we also have a linked list that stores all those cells that haven't been exposed so that we can traverse it without going through the entire matrix. And so it turns out that these data structures satisfy some consistency properties. In particular, there are properties of the list that prev is inverse of next and that next is acyclic. But there are also properties that correlate different kinds of information about the cell objects. Namely, it turns out that object is in this hidden cells list if and only if it is initialized and its exposed flag is set to false. So let's look how we can verify such consistency properties that correlate different kinds of information. So the first step is to somehow formalize this property, and we're going to formalize it as an invariant, namely as an expression that is true whenever program reaches certain program points. And so this is how I formalize it. Basically, I want to say that the set of objects that are in the hidden list, in the linked list, is equal to the set of objects that have certain values of flags. And the way I'm formalizing the set of objects that are in the list of hidden cells is by using a reachability expression, basically saying there are those cells that are reachable along the next field from some route. And so the difficulty in statically verifying such a property is that we need to precisely track reachability properties, namely whether something is in the set of reachable objects or not. And then we need, in addition, to correlate these reachability properties with values of Boolean flags. So the approach that I'm going to take is actually to refactor this complex invariant. How am I going to do that? Well, I'm going to give names to these sets. Namely, we have a set of objects that are in the list. Let's call it list content. I'm going to give name to the other set, the set of unexposed cells. And so now what we want to do is we want to prove that these two sets remain equal. And the way we would like to do that is by not worrying too much about how they are defined. So most of the time we wouldn't like to depend on how these sets are actually defined. So how are we going to do that in the actual program? Well, let's look at the source code of Minesweeper. So we have some record declaration that introduces these data structures that I described. And let's look at one operation, expose. This is what happens when you click on some cell. So what the program needs to do is to remove the cell from the linked list and to set the appropriate flag. And I wrote here removal from the list and setting of the appropriate flag. And the first step in our approach is to encapsulate the complexity of individual data structures into modules. So we're going to introduce two modules, a list module that manipulates the linked list and board module that manipulates the values of flags. And then we can factor these data structures into appropriate modules. So we here use a notion of partial record, which you can think of as an open class or partial class. And then we put appropriate operations into these modules, right? The operations that manipulate that data. And so now that we have done that, now that we have encapsulated the data and operations in these modules, we are now in position to replace these implementations with their abstract specifications. So the result will be that, for example, remove operation will be described by a set of objects, namely by an effect of a set of objects that we call content. Right? So we've introduced this set of objects, and now we can say that the remove simply changes the set in such a way that the set after removal is equal to the original set minus this object that is being removed. And similarly, the other set, the set of unexposed cells, is changed by removing an element. And now we can reason about these. We can reason about whether this invariant is preserved using sets alone. Because if we are analyzing the expose procedure, then we see that it's going to remove the element from the first set, and then when it calls the remove operation, and when it calls the set flag, it's going to remove it from the other set. So you can see that basically this equation is still preserved. Yes?
I'm sorry, just a high-level question. Will this technique work when data structures have shared cells, or is this only really reasonable when you have something like a separation logic where you can really separate the heap into disjoint parts? So for example, if I have a sparse representation of a matrix as linked lists, they might be linked across in rows. Well, maybe that's not a good example, but I might have data structures. I might have cells in lists. We see this in device drivers, which are part of multiple linked lists.
Yes. So in fact, in Minesweeper, we have such data structures.
Okay.
And it turns out the reason we can do that in our language, so this is all implemented in our language, that you could sort of do that in Java, as I'll mention later, is because we are separating things along the field. So you could have the same object that is member of multiple data structures, and the way you can achieve separation is by basically using disjoint sets of fields to implement membership in different data structures. So, as I suggested, now we can actually reason about data structures in an abstract way using solely sets of objects. And this basically motivates the two parts of our modules in our system. So we've seen that we have implementation, which is the standard implementation as you would have in an imperative programming language. But now we also have specification in terms of set. So we can this specification enables us to reason about the behavior of the procedure. But the question is, how do we know that this implementation conforms to the specification, right? And what does it even mean that that there is some conformance if this is expressed in terms of one kind of data, namely in terms of the set, and this is expressed in terms of some next and prev pointers. So in order to justify this reasoning, we would need to somehow know that implementation conforms to specification. But this is why we have the definition of the sets. So, and this, if we do that, if we have these three parts, basically the specification, definition of the set, and the implementation, then you can see that the high-level invariant, together with definitions, actually gives us the original detailed invariant, right? So if you take these two together, we get what we wanted to check initially, and we have essentially modularized this high-level invariant by putting its parts into appropriate modules. So what that means that in our system we have the implementation section of each module, we have an abstraction section of each module, and specification section. And so specification is used when reasoning about the module from outside, implementation is what actually executes, and then abstraction section connects the two. And so this is what you would actually write in our language for a fragment of a list implementation. So you have the more or less standard implementation. Then you have a specification, which includes contracts for procedures. So you have a abstract, or you could call this a model field of a set type. And then you express that remove operation has a precondition that element must already be in the list and it cannot be null. And then the operation modifies the content in such a way that it removes the element. And then, as I mentioned, there's this abstraction section module that gives the abstraction function that makes the connection between two. And in addition, it's going to specify this invariant. Basically, so we now need to show that implementation conforms to specification in order to justify this high-level analysis. And while we are doing that, we are also going to verify these invariants. So there are these internal data structure consistency invariants that are specific to the module. And the nice thing about this modular approach is that you only need to verify them inside the module, and you know that they will not be violated outside. And so in this process, note that when we verify that the implementation conforms to specification, we are both justifying the analysis of clients, because it means that the client is entitled to use this specification, and also we are proving partial correctness of the implementation, because this is a nice description of what the remove does. Basically, it tells you that it removes an element from the set. And so this is a summary of our approach. We basically have two steps. First step is reasoning about programs in terms of simpler structures, and this is where we are verifying the uses of data structure interfaces and relationships between different data structures. And here's where we can hope to use more scalable analysis, because we don't have to worry about implementation details. And then we have the other step where we check that implementations conform to interfaces. And this is where we use these precise analyses that need to track these linking relationships between objects. But note that we are only using them in the context of individual modules, as opposed to running them on the entire application. Yes?
So if you have a higher program, a lower program, and they work in lockstep.
So what is really happening is we have the program that executes as it would normally, but for the purpose of reasoning, we do it this way. And you could imagine, for the purpose of correctness argument, that there is a sort of abstract program that executes as well. But this is really just your entire module. Basically, these implementations here and implementations on the client side is what is really executed, just like before.
Nevertheless, in the imaginary world,
right,
you have a more abstract program, and more concrete, and in this example, they go lockstep.
Yes.
Many other refinements say don't have this lockstep. They even have more steps.
Right. So this is a special case of sort of using refinement relations to show the conformance. We found that for these data structure consistency properties, abstraction functions were sufficient. So this pretty simple correspondence in terms of the if you look at execution traces. But the complexity in our case is definition of the abstraction function itself, namely that it needs to talk about reachability properties. So there isn't as much complexity in the actual dynamic part as there is in the sort of complexity of the state that we are abstracting.
Make a remark. The upper program in this example is not executable.
Yes.
No, it's create post condition only. It's not executable. It's a constraint.
New content gets old content minus this object.
No, but it expresses and ensures. It's a post condition. It's not. It's
right. So in this context, we do not require these contracts to be executable. They are formulas in Boolean algebra of sets. And so this is actually what brings me to the next point. So first, let me just note that this approach does have the promise to address both scalability, because we are using these analyses that deal with sets only, heterogeneity, because we can use different analyses within to verify implementation conforms to specification, and it also addresses precision, because we can use these precise analyses in modules. And finally, we can use these interfaces to communicate some user-specific, application-specific properties to the system. And so this is, of course, an approach that's been used under the name of data abstraction in systems like ESC Modular 3, ESC Java, and Spec Sharp, and also in systems like VDM. But what is specific to making this approach automated is basically how do you choose this interface language? And so in the first project that I'm going to talk about for most of my talk, we actually used set algebra as the specification language. And so this, what do I mean by that? Well, we can use set algebraic expressions like intersection, the subset, union, and so on to express high-level properties between data structures. So we can talk about two data structures being disjoint, one being included in the other, or we can also express some more precise properties like insertion into the data structure or removal. And so this is why we think that this specification language is both useful and verifiable. So it's useful because it can express these properties as well as conceptual properties that talk about type states of objects. So these finite state properties that I mentioned, there's a lot of work on. And it can do that by saying that basically an object is in a given type state if it's a member of a given set. So changes in type state correspond to removals and insertions of objects to and from sets. And then, so it's nice in that this language can express some relevant properties, but it's also verifiable. Namely, we can use these type state analysis techniques at higher level, or their generalizations, and we can use shape analysis at this lower level to show that implementation conforms to specification. And so this is what we exploited in our system. So we actually built two systems, Hub and JHub. That the Hub is the first system that I showed you example in, and JHub is an ongoing work in the context of Java. And so there are several components of building such a system. One important component is decision procedures and theorem provers, because they're what enables ultimately the reasoning. And here we implemented an interface to interactive theorem prover, which allows us to prove arbitrary complex properties, but in general it would require a lot of interaction. So we also then implemented interface to a MONA decision procedure that enables reasoning about these reachability properties. And then in order to be able to analyze a much wider class of data structures than would be possible using this decision procedure alone, we implemented field constraint analysis on top of that. That is sort of you can think of it as pre-processing step, but it's really allowing a larger class of data structures to be handled. And so in addition to that, we worked on some decision procedures that combine reasoning about numerical quantities and reasoning about sets of objects. And then these decision procedures would allow you to reason if you have something like loop invariants, so certain annotations. And so we also then have annotation inference algorithms that allows developers to avoid writing annotations in most cases. And so here we developed different in loop invariant inference algorithm for this high-level analysis, and we have a different algorithm for the implementation for analyzing implementations of data structures and inferring loop invariants inside them. And of course, then there's some work in actually designing the infrastructure and the modular verification technique. So one of the goals of this infrastructure is that you can use these different loop invariant inference techniques and different decision procedures, and you should be able to sort of mix and match them and get different sort of analyses effectively. And of course, you should be able to use them at the same time as well in order to analyze larger classes of programs. And so what I'm going to do is show you sort of one slice through the system that you can view as one shape analysis. Basically, it has invariant inference and field constraint analysis along with MONA decision procedure that allows us to analyze linked data structures. And so we call this analysis BONE. This is joint work with Thomas Wies and Andreas Podelsky. And so this BONE analysis allows us to analyze linked data structures like lists and trees. And its feature is that it can precisely handle reachability properties. And that's important because it allows us to abstract this recursive linked data structure into the set. So we can define the set of objects as a set of objects reachable from the root. And we can quite precisely reason both when something is reachable and when something is not reachable. And because it's based on decision procedures that are complete for a given class of formulas, we can basically have a predictability of the analysis, which says that if either we'll get a back answer that the data structures are consistent, or we'll actually know that there exists a counterexample. And so let's see how we would start building such an analysis. Well, if we have a decision procedure, turns out you can encode loop-free code fragments into the logic of this decision procedure. Then you can use a verification condition generator and get a simple analysis. So what would such analysis do? Well, it would take contracts and implementations of each procedure, and it would create these verification conditions, which are just formulas that say if the precondition of the procedure holds, then after you execute the body, the postcondition will hold, and while you do that, there will be no runtime errors. But the main thing is that the postcondition will hold. So you can create such a formula by syntactically translating the body of the procedure, and of course applying abstraction function as well. And then when you have this formula, then you give it to decision procedure. If decision procedure says that the formula is valid, then you know data structures are consistent. If it says that it's valid, then you know that they are not. And so the real question is, what decision procedures can we use? Well, in order to reason about reachability properties, we use monadic second-order logic over trees. And in fact, we used existing MONA decision procedure for this logic that's based on tree automata. And what this allows us to do is to analyze implementations of tree data structures. And that's nice, but if you add, for example, parent pointers, you couldn't directly use this decision procedure because it's not a tree. Parent pointers introduce cycles. And so what we have then, we have this field constraint analysis that I'm going to tell you about now. And that enables us to reason about non-tree fields as well. So we can handle, thanks to this analysis, also doubly linked lists or trees with parent pointers. And what is also interesting for this particular approach is that we can handle those data structures where these additional pointers actually are not uniquely determined by the other pointers. So the idea is to have some tree backbone. In this case, it's a list backbone. I'm showing a two-level skip list. And then in addition to tree backbone, you have these constraint fields. And so these constraint fields are actually given by a formula in terms of these backbone fields. So in this case, constraint field simply points some place forward. So that actually happens for skip list, that you don't know exactly where you point because it's a randomized data structure where you decide with some probability whether you are going to insert something into the other list. And you still have some invariant on this constraint field. Namely, if there is an edge from one object to the other, then you know that there is some path along the next fields, but you don't know how long that path is.
You also don't know the height of the tree, right?
You mean height of the skip list. So I'm not talking just about two-level skip list. So actually, I'm not analyzing n-level skip list because it would require an array or so. N-level skip list is currently something we have not pushed through our approach yet.
But it's more also, right? It's the second level doesn't cross, that just cross.
Yes, you could state that as well. I mean, you could, in principle, state a conjunction of constraints where you say that the second level is a list itself, right? And so it's sort of two independent properties. Yes.
Okay. How do you deal with arrays?
This is something more recent. So we've only recently started analyzing arrays. But so what I'm going to talk about here is focused on linked data structures.
I just have a sort of high-level question. I always used to think that arrays are simpler than linked lists.
Yeah, that's why we handle the harder cases.
I see. So, but do you think that it's just like this? You'll be able to handle arrays and linked lists together, or is there some complexity there?
Depends. If you look at hash table, there are some interesting additional techniques that you would need to use. So hash table is one interesting challenge benchmark, I would say, because especially you want to analyze hash function as well, sort of prove some basic functionality properties of it. And so also, if you have instantiatable data structures, this is something that we've been working on only more recently. Basically, what I'm talking about here in the first system is for global data structures.
Did you analyze any examples where you had to write a significant chunk of annotations stating non-aliasing properties? This often happens when you have sort of container objects, right? So every object in a collection has a reference to some other object. And one invariant is that all those reference point to distinct objects. Right. So do you have any experience with those kinds of things?
So if you have global data structures, that is usually not an issue because you have a single root. But in general, the way we have been addressing these constraints is by using a requirement that the backbone is a tree, and then you get the uniqueness as a consequence of that. But you might imagine wanting to use something like unique pointers for some of those examples. So, but if you have a tree backbone, for example, if this was stored in some data structure, you would have the first pointer here, and then perhaps you would have data pointers. So one thing you could say is that this first pointer along with the next forms a tree backbone, and then you would get uniqueness of that field. If you see what I mean?
Perhaps you can talk about.
Okay. So some of the aliasing, because this analysis is focused on tree-like data structures, part of the specification rules out aliasing in some cases.
Quick question. You said this magnetic second order procedures for finding trees, they are complete, but aren't they excessively complex?
They are non-elementary in general. I think that in practice we are not running really into non-elementary behavior. We are running into exponential behavior. So typically formulas have a bounded quantification, about the number of alternations that we're looking at. So, but yes, we have found that analyzing data structures that are truly trees, where we need to use tree automata, is significantly slower than analyzing data structures that can be handled using ordinary finite state machines on words. So for example, Mona works much faster on list-like data structures. And so in some sense, some of the approach that I'm going to talk about later on is independent of the decision procedure that you're handling. But I thought it was interesting to present this one because it shows that there is a large class of data structures that you can handle by using Mona with some approach to eliminate these field constraints. And it turns out that it terminates in practice for these if you use it on small pieces of code. And so what do we want to do now? If we want to analyze such data structure and ultimately using monad decision procedure, we have our field constraint analysis takes a formula that has both next and next subfields, these derived fields, and produces a new formula that has only the next field. And then we have the property that if this formula is valid, then we know that the original formula was also valid. It just means that our translation is sound. But the interesting thing is that we also have that if the formula is invalid, then in some cases we can prove that if the resulting formula is invalid, the original formula was also invalid. And so this class of constraints for which this is the case is basically where these derived fields in verification condition appear basically in an essentially quantifier-free way, but they can be universally quantified because it gets columnized. So, but basically, what that implies is if you want to preserve the fact that field constraint is valid, basically, so you're assuming this field constraint, and that's how you're reducing this formula to the one without the constraint fields. But you also would like to reestablish it so that you know you can rely on it subsequently. And reestablishing these field constraints is a formula of that form, so that we are basically complete for data structures that maintain these kinds of invariants at loop boundaries. And so this is one of the difference with previous approaches is that you could also get completeness, but only when this the approach was only applicable if the constraint fields were uniquely given by the other field. So you couldn't write some arbitrary formula here, where here in principle you could write even true if you wanted to. And so this is sort of the description of what you would do if you had only verification condition generator and some decision procedure. But as I mentioned, you would like to infer these loop invariants so you don't have to write them manually. And so I'm going to tell you quickly about loop invariant inference. So the main challenge here is, as you might guess, is that there are infinitely many possible heaps. Here I illustrated possible states at the entry of the remove procedure. And so because you have unbounded number of objects, our approach is to partition these objects into sets, to some equivalence classes. And the way we do that is because we want to track reachability, is to basically to group objects according to whether they're reachable from certain routes. So in this case, we're going to introduce the set of objects, property of being reachable from the root, and property of being reachable from the parameter variable. And if you partition objects according to these predicates, including the ones being directly pointed to by variables, then you get something like this. So, for example, you get here a potentially unbounded number of objects, but all these objects have the property that they're reachable from root and they're not reachable from the parameter variable. Unlike these, there's also a potentially unbounded number of objects here, but they are all reachable both from the parameter and from the root. So according to reachability, you can partition the objects in the heap, and then we get what we call abstract heap. It's basically given by some set of objects and properties that they satisfy. And so this, there are many ways of defining these domains for inference of loop invariants, and we will look at some graph-based approaches, and we show that in some cases they might have undesirable properties. And the approach that we adopted here is based on partitioning according to these properties and has some very natural sort of description in terms of formulas. Namely, it has the following form, which means that you have these properties according to which you are partitioning. And they are, of course, unary predicates on objects because there's either hold or don't hold about any specific object. Then when you take their conjunction of these properties and their negations, then you get this individual summary node. And if you take multiple summary nodes, then you get abstract heap. And the abstract heap basically says that every object in the heap satisfies one of these properties. And so this is the key abstraction, and you can have multiple possibilities at any given program point. So about what the abstract heap could be, basically what could the possible states at this program point be. So you get formulas of this form, and if you compare it to something like predicate abstraction, you can see that in some sense it generalizes it, but by introducing these unary predicates, and it's therefore related to index predicates approach. But we have here universal quantification over the resulting Boolean combination, and then we have additional disjunction here. So this is the domain that we are using. And so we found that this gives us ability to control both precision and efficiency in the analysis. So the key question then is, if we have this abstraction, how do we analyze the program using such abstraction? Well, the goal is to explore possible configurations, and by analyzing the effects of states on some initial set of abstract heaps. And so the effects of statements turn out to be computable using essentially verification condition generation and theorem proving. So we have a finite state space, and the way we are going to explore these transitions in the finite state space is again using something like the approach that we had for quantifier-free case. So we have two formulas, and then if we give two formulas and the basic block, or you can think of it as just one statement, then we can compute a verification condition generator, give it to decision procedure. If it says that this is a valid verification condition, then we know that transition exists. And if it's invalid, then we know the transition does not exist. And so this would be a naive approach that you would end up calling this expensive decision procedure doubly exponential number of times. So what we do in practice, we exploit the structure of this domain a little bit more. So we basically use some approximations, and we try to avoid the recomputation as much as possible by sort of creating a transition system that is abstraction of the given program, and then exploring, finding fixed points in this transition system. The complication is that unlike predicate abstraction, we need to occasionally recompute this abstract transition system. And this is even without inference of these predicates. So currently, by the way, an important question is, where do these properties come from? So one source of these properties according to which we partition the heap are actually these abstraction functions. And another source you can derive sort of in general, knowing that reachability properties from local variables are important. And then we also have ability for developers to specify some additional properties, which is still less work than specifying invariants. Okay, so I gave you an idea of how one analysis in my system works. And in addition, I mentioned there's this high-level analysis that I don't think I will have time to talk about. And I mentioned that if you have really complex data structures, for example, we had priority queue implemented in an array where we had some integer arithmetic and some divisibility constraints. So we verified that using generating verification conditions and using interactive theorem prover. And these interactive theorem provers are getting better every day, so this is not as bad as you might think. But so let me tell you which programs we've analyzed. Or what our experience with the system was. I mentioned the Minesweeper example, so we verified all these properties in it. In particular, you can see that some of these properties you could actually tell to someone who is even playing the game or developing the game. So basically, we verified disjointness of two sets of objects that indicates that a cell can never be both hidden and exposed. And perhaps more interestingly, basically a partial indication of the termination condition for the game. So if you have, if two sets are not disjoint, if the set of cells that have mined and set of cells that you've exposed have an element in common, then the game is over. So these kinds of properties we were able to verify by abstracting the contents of data structures and then using the simple language of sets. And we also verified lists with built-in cursors. You could think of this as a special case of an iterator. So you define, here's a linked list, and it has a private current pointer. And the way you specify it, you say there is some set of objects in the list, and there is a set of objects that still remain to be iterated over. So you have this simple description that has two public sets and one invariant about them. Namely that a set of iterated objects is subset of the set of the content of the list. And then we verify we have an implementation of this linked list, and we can verify that it satisfies the contracts expressed in terms of these two sets. So in particular, when we were verifying the remove operation, turns out that there was this condition was violated that I meant to be true, and that was because I forgot here to bump the current pointer when I was removing an operation. So you can see here that such set interfaces tell you what happens to the content of the data structure and also tell you what happens to the iterator. And so then once you verify the implementation, you can verify usage protocols of such data structures. So you can verify that when you're calling next iterator, there are still elements to be iterated over. And when you go through the entire loop, iterating, you know that there are no more elements to iterate over. So such sort of data structure usage protocols can be verified. And then we analyze some other programs. So we analyze water simulation benchmark where we check that ordering of phases is the one that you would like. Also, we have this website actually should be running on the web server that's written in our language and then translated into Java. And so here, as I mentioned, both we verified some high-level properties and properties of individual data structures, such as the ones that you've seen. More recently, we started with arrays. And indeed, in some sense, the arrays are simpler. But then when you have both lists and arrays, you can construct more complicated data structures. So we are looking forward to verifying some of those. And in ongoing work, we are actually verifying some more complex games. And we were playing with some parts of operating system data structures implemented in Java. And this ongoing work is in the context of the new system called JHub, whose idea is to basically check data structure consistency properties in a wider range of scenarios. Basically, we want to verify not only set interfaces, but also relation interfaces. We want to specify basically containers that have an unbounded number of instances, and we want just a richer specification language. So here the implementation language is a subset of Java, and the specification language is actually a subset of the Isabelle interactive theorem prover. And so we are in this context, we developed some new decision procedures, and we are planning to incorporate more of them. So the idea here is also to combine these decision procedures in a more fine-grained way. As opposed to using different decision procedures in different analyses, you want to use all of them at once. But I'm going to tell you about what can you do if you use more of them. So in particular, what you can do is verify implementations of relations. So you have here a relation in that diagram that I showed you, but perhaps it's implemented as a binary search tree that maps keys to values. And there, it turns out you can use monadic second-order logic over trees to verify sort of this part, and then you can use first-order reasoning to verify the local relationships between keys values and the objects that point to both of them. So this kind of combination allows you to verify more properties. And so we are looking at verifying implementations of relations, but also uses of relations. And here's where sort of verification of these cardinality constraints comes from. And we think that using some class of first-order logic and using two-variable logic with counting or description logic is a promising approach in that direction. And of course, one important question when moving to Java is having modular methodology that supports the common patterns in object-oriented programming. And so among the decision procedures that we are looking to integrate in, I would like to just mention Boolean algebra with Pressburger arithmetic, because that's something that allows you to integrate reasoning about these numerical constraints and the number of objects. And so you can say that, for example, two containers have the same size, or the size of a container is equal to a given size field. And here's the way Boolean algebra with Pressburger arithmetic looks like. So if you know what Boolean algebra is, you have these set operations, and there is linear arithmetic that's called Pressburger arithmetic, and you can have arbitrary quantifiers. So both of these are individually decidable. It turns out that if you put them together, they're also decidable by quantifier elimination, even if you have this nice connection between them. So this is what makes it interesting. You can take size of the set and treat it as an integer. And so that's actually the decidability of this is a result by Pfefferman and Watt. And so what we did from 1959, it was mistakenly stated as an open problem recently. But actually, it turns out that if you analyze the algorithm for that, if you write it carefully, you can prove that it has about the same complexity as Pressburger arithmetic itself. So it's doubly exponential or triply exponential upper bound. And so we show that this is the case. And then we also have more recent results that talk about quantifier-free case for this algorithm. So a quantifier-free case is something that a naive algorithm would give you non-deterministic exponential time, but it turns out you can do it in polynomial space. And then we also have some more restricted fragments that are actually polynomial. And so this is what I wanted to tell you about the Hob and JHub systems. I'm going to now just mention some future work where basically you can view this part of this line of work as showing that some implementations satisfy their specification, or basically showing that some models of the system conform the models are implemented correctly in implementations. But what I would also like to do is focus on the verification of models themselves. So models in some sense are just specifications. So I use these two things interchangeably. And so I had some experience in sort of extending the applicability of existing model finders to analyze potential infinite domains. And another thing that I would like to do is, once you have these specifications, to make as much advantage of them as you can, basically, both using runtime checking and being able to sort of do test generation from them, or use them as a source of test cases. And so one question in runtime checking is basically executing these non-deterministic specifications in an efficient way. And there are some issues that you could work on towards making it easier for developers to adopt these specifications. I think that's also important to keep in mind. And more generally, I think that if you look into the future, if you want to create systems that are going to help in software development process and make some really sophisticated decisions, you'll have to make them domain specific. So that's where the cases in which the systems will be able to be both tractable and make some sort of sophisticated decisions on their own. And so I have some related work slides, but I'm just going to say that this work is building on sort of type systems and type state systems, and it's sort of on the more precise side of some data flow analysis, like pointer analysis and analysis of arrays, and it's directly relevant to the work on shape analysis that's been very active recent years. And as I mentioned, model checking is more focused on finite state systems with controls, and predicate abstraction is something that enables the use of some of these techniques by translating the complexity of data to finite state systems. And of course, there are other approaches that do not necessarily guarantee soundness, but I think they're valuable in terms of finding, for example, you could use them to find candidate loop invariants, and of course, to find bugs before you even attempt to prove that the program satisfies certain properties. And this work ultimately relies on decision procedures and theorem provers. I think this is what really will enable us to handle larger classes of properties. And so, of course, if you shoot yourself in the foot in terms of programming language that you use, you won't get very far. So I think that having appropriate methodology and appropriate sort of frameworks that have been developed in the context of full program verification is very important. And some of the recent work has been towards making these approaches more practical. And so let me just conclude. I described an approach to statically verifying data structure consistency properties. I talked about the hop system that has a framework, a language, and static analysis, where we deploy the shape analysis and a high-level analysis, and we analyze some programs such as Minesweeper, water simulation benchmarks, and web server. And in the context of these systems, we analyze both high-level properties like relationships between data structures and also detailed properties inside the data structures. And the ongoing work is to push some of these ideas in the context of Java, where we have a more general class of problems and richer scenarios of using data structures. Thank you everyone for listening.
Let's take some questions.
Yeah.
So, you've split the verification problem into several modules, for example.
Yes.
So that you can for each of the modules apply a different kind of analysis. If you were to break open those scopes so that you had everything in the same scope, take that Minesweeper example. For example, when you split the code into several modules, suppose that you had not split the code up into those modules, or maybe just had all of the declarations lying around in the same scope, then would it be the case that the individual analyses would get confused because of the other code, or couldn't work, or would they just sort of automatically ignore the rest of the program? I mean, how essential is it that you break it up into modules first?
So in the original system, we intentionally developed a methodology so that the programmer is aware of the fact that they would like to separate the concerns. And then the system was built so that it applies only one analysis to one procedure. So potentially, if one procedure if the analysis would need to look at detailed properties of multiple data structures in the same procedure, it would simply have to ignore some of them because you would only use one of them. This is of course not essential, and this is just in some sense simplifying assumption that we made initially, and it is not the assumption that we are using in the new system. The question is whether that's useful or not. I think it is useful if it's useful to provide the mechanisms for developers to enable such separation, because it does sort of, as you suggested, prevent the analysis from getting confused. And for example, the question of combining these logics is that you may need to use non-trivial analysis in order to separate different parts of verification conditions. So if you are trying to use Nelson-Open, where you have something like an entire Boolean algebra being shared, you would potentially need to guess an exponentially large object. And that's why, for example, in Boolean, the quantifier-free Boolean algebra with Pressburg arithmetic, a naive algorithm would be non-deterministic exponential time. So what we found is that if the developer suggests some information about this separation, even if it's not across modules, it might be by stating certain lemmas, then this we basically can use very simple approach to combine decision procedures, where we simply use different decision procedures to discharge different sub-goals.
Any more questions?
In stating all of these properties to be proved, both writing the specifications at the source code level and translating them into different analyses, do you have some common expression language or common framework that all of them can share, or do you have to have special procedures before going to a particular analysis that takes a separate input and
so that's actually a very good question. Basically, how do we communicate between different analyses? And in the first system, Hob, because it has such loose coupling of the analysis, the only communication is through the set specification language. So basically, the communication is at the boundaries of procedures, and the analyses that we actually use do have different representations for the formulas that they use. So, but we did need to use sometimes translation from this set specification language, because they were just syntactically different. Now the story, basically the story is that we have looser coupling, and therefore we are only communicating through set specifications in Hob. In JHOB, we are basically using one internal representation language, which is a subset of Isabelle formulas. And this is what enables us to combine these decision procedures even within individual verification conditions. So it's really a combination in JHOB is more at the level of decision procedures currently.
So then let's thank Victor again. So.